are going to do experiment 7. So experiment 7 is about electrochemistry. So in this electrochemistry, basically we are going to learn about redox reaction, oxidation and reduction reaction. So depending on the metal reactivity series that we have already seen in the class, so we are going to see that the more reactive metals are going to replace the less reactive metals. So here we have copper strips, zinc strips, magnesium strips and also lead strip. Okay, so we have these 4 metals and we are going to determine by using this electrochemical reaction which is more reactive. So the first set that we are going to look at is the copper and zinc solution. So in this beaker I have a solution of zinc nitrate, and in this beaker I have a solution of copper nitrate. So what I'm going to do, I'm going to take the red color is the positive terminal and the black color is the negative terminal. So I'm going to take this red color and first place it on the zinc strip. Alright, and then the second one I'm going to place it on the copper strip. Alright, okay. Before we proceed, we need to connect these 2 beakers, right? So when we want to connect, the first thing that we have to do is that we have to build a salt bridge. Okay, so how do we do this salt bridge? We are just going to take a piece of this filter paper cut like this, and then we are going to dip it into the potassium nitrate solution, and then we are going to gently lift it and put it inside so that the filter paper actually touches both the solutions. Alright, so this is going to act as your salt bridge. So you should find out what is the function of the salt bridge. Alright, so now that I have the positive terminal zinc and negative terminal is copper, I am going to dip it into the solution zinc and copper solution. Alright. If let's say the reading of the voltmeter becomes negative, I am going to quickly switch the electrodes. So let's see whether it becomes positive or negative. Me too. Okay, so we can see that the value is a positive 0.95. Alright, so the next pair that we are going to do is the magnesium and copper pair. So I am assuming that the positive electrode should be the more reactive metal. So I am going to place the magnesium in the positive electrode. So let's hope that it works and we get a positive value of the reading. So I'm going to dip the magnesium into magnesium nitrate solution and copper into the copper nitrate solution. This is not copper, sorry. This is copper. Okay, so I'm gonna put the magnesium inside magnesium nitrate and copper inside copper nitrate. Oh, forgot the salt bridge. I forgot the salt bridge, so that's why we couldn't see anything. Place the rods inside and we are going to observe the voltmeter. Okay, so we can see that the voltage is going up to 0.87. We are going to test is the plumbum and the copper pair. So as usual, I'm going to dip it into the potassium nitrate solution, and then I'm going to place one end of the salt bridge into the beakers. Make sure that the paper is touching the solution, and then I'm going to clip the positive side to the plumbum and the negative side to the copper, and I'm going to place them into the solution and observe the voltmeter. So we can see that the voltmeter is still positive. It's showing 0.503. Okay, I'm assuming that the magnesium is more reactive than the zinc. So I'm going to place the positive as the magnesium and negative as zinc. Okay, so I'm going to dip the magnesium straight into magnesium nitrate and zinc into the zinc nitrate. And yes, we are correct again. So 0.689, 0.69. Okay, I think magnesium is more reactive than the lead, but still let's try what happens if we place the magnesium into the negative pole and lead into the positive pole. Okay, so I am going to place this, and then when we see the voltmeter reading, it's immediately dropping to negative. Okay, so the more reactive metal should always go into the positive electrode, and the less reactive metal should go into the negative electrode. Alright, I'm going to dip it in, and then we can see that the value is positive 1.0.